you go to the top of Mount Everest, it's 8 kilometers away from the surface of the Earth. Your force of gravity would be smaller, like 9.7 something meters per second squared. So the fact that gravity is stronger at the bottom of the ocean doesn't mean anything because you're underwater, but just because you're closer to the center of the Earth. So the distance you are away from the center of the Earth affects your gravity. How fast is terminal velocity? Sorry, getting back to your question. Alex, terminal velocity depends on lots of things like how much air resistance you have, your surface area, and things of that nature. So a piece of paper's terminal velocity is, we watch that paper kind of float down. If I dropped a penny, it would have a different terminal velocity. So terminal velocity is a function of how much surface area you have. When you see skydivers, they jump out of a plane, they do this kind of like starfish thing so they can control their descent. And then if you've ever seen like action movies where the skydivers do this like tuck and they put their arms down and they do this kind of like thing and they speed up all of a sudden, you have a big surface area like this, you have a small surface area if you tuck your arms in. So a human can have a different terminal velocity depending on what their shape is. So terminal velocity is just basically when the air resistance kind of equals out with the force of gravity. That's when you reach your terminal velocity. Water pressure and gravity have a relationship. Yes, but not the way you're thinking, Ava. Water pressure and gravity have a relationship because they're both forces. So not water pressure, but buoyancy. Buoyancy is a force and gravity is a force. So we can compare them just like we can compare the force of magnets. Magnetic force, that's a force. So a force is anything that's a push or a pull. So because buoyancy pushes you up, gravity is pulling you down, those are forces, and we can calculate the total force of an object. We could put a magnet next to an astronaut or below them, and the metal in their suit would be sucked down, and then we'd have to give them more buoyancy, displace more water until they kind of got that weightlessness. So just getting to the idea of forces in general. So a baby would fall faster than a sumo wrestler because the baby has a smaller surface area. Yes. I don't know why we're thinking about babies and sumo wrestlers skydiving or falling, but that is true. I don't know if fall faster is a word I would use. I would say something like, you don't want to use the word fall faster because it's implying that the acceleration is different. We're talking about terminal velocity. So a baby would have a higher terminal velocity, it would be faster than a sumo wrestler just because they have a smaller surface area for sure. Could you jump slightly higher at higher altitudes? Yes. Just like if you've ever seen footage of people walking on the moon, the acceleration due to gravity on the moon is about 3 meters per second squared instead of 9.8 like on Earth because the moon's much smaller than Earth. And you can see the astronauts kind of bounding around and it kind of looks like they're walking on a trampoline just because the force of gravity is a lot smaller. So you could run and jump and you could, go a lot further on the moon than you could. Or if you've ever seen a movie like, what was the movie? Armageddon? I think they're on like an asteroid and Armageddon did a famously bad job of the physics of being on an asteroid. Asteroids are very small, wouldn't have a very strong force of gravity, but they're all kind of driving around and walking on the surface of this asteroid like it's just nothing. So there you go. On a plane, well, you could do a calculation. Take Physics 11, you could do that exact calculation. You love that movie. How come the moon hasn't smashed into the Earth from Earth's gravity pulling the moon? Because the moon is in orbit. So it's not falling. If we stop the moon, it would fall into Earth and that would be bad. But the moon's actually in orbit. Just like, this is completely off topic, but this is the most misunderstood concept by the general population in terms of space, in my opinion. Astronauts in space, they're in space. They're above the surface of the Earth. Let's say they're 100 kilometers above the surface of the Earth. Well, they're above the surface of the Earth. They should feel the gravity of Earth. Why don't they? Well, they do, but they're in orbit. So they're constantly falling towards the surface of Earth, but in a circle. So they never reach the surface of Earth. So astronauts if you were on the International Space Station and you could stop the International Space Station, so stop it from moving and just kind of hover it above the surface of the Earth, the people in the space station would feel gravity. They could walk around. But because the object, the space station, is constantly falling towards the surface of the Earth, it's in orbit, they feel weightless. Just like if you were to be taken up to in a plane, and I put you in an elevator and I push the elevator out of the plane, you would feel weightlessness. You couldn't see out, you couldn't see you were falling, but you would feel weightless until the elevator hit the ground. Now, if you're in the plane and you're in an elevator, the plane's holding you in the air through the buoyant force of the wings in the air, but you could stand on the bottom of the elevator and you'd feel the force of gravity in a plane. That's normal. But if you throw the elevator out of the plane, it starts free falling, you'd be weightless until you hit the surface of the Earth. So this is how they simulate gravity on space stations in orbit. Now I'm getting really, really off topic. That's okay, it's okay. We're almost done the course. How do they simulate gravity on space stations in orbit? Our space station doesn't have any gravity simulation. What we could do would be to make a big kind of revolving ring. If you've seen the movie The Martian, their Mars orbiter thing has a big ring that spins. And because it's spinning, it causes something called centripetal force. And that causes you to be able to, walk around. When the astronauts train to go into outer space, they take a 747 or a 737, a big jet. They take all the seats out of the inside of it, and the jet flies up into the air, and then it dives back down. And it's called the vomit comet. And as the plane gets to its highest point, you get weightlessness, and then it kind of free falls. So it accelerates downwards at 9.8 meters per second, so the astronauts feel weightless. And you can go on the vomit comet, and you can feel weightlessness for short periods of time. So the plane just constantly does big parabolic arcs. And you get to the top, you feel weightlessness, the plane accelerates down at 9.8, you get weightlessness, and then you get gravity again, and then weightlessness and gravity, and you just keep doing that. Could they put magnets in their shoes? Magnetic force is much weaker than the force of gravity. It's relatively a weaker force. So the force of gravity isn't as much stronger than magnets. Magnets work in space. Yes, they do. Magnets work everywhere. All right. Well, that was a good waste of 10 minutes. Not a waste. Very important 10 minutes discussing topics related to science, astronauts, things like that. I said I'd do some more of those two-step problems, but what I want to do is finish the course. You see, 9.2, also known as the end. So this is the end of the course. Ava, I've taught Physics 11 a bunch of times, and these are all kind of Physics 11 type concepts. And when you find stuff interesting, you just remember it. It's just kind of cool stuff. Students always ask the same sorts of questions, so you get used to answering the same sorts of things. Now you know, and you'll remember it, you can talk about it. People that are interested in sorts of stuff. So what I'm going to do is I'm going to power through 9.2. Got about 20 or so minutes to get through it. And then we are going to, oh Alex, there's lots of science left. What we're going to do is we're going to get through 9.2. That's the end of the new material. So today is the last course for this, or last class for this week. Next week we'll have class on Tuesday. Wednesday we're going to go to KSS and do a lab at KSS. Very excited about. And then we're going to just continue, like next class we'll go over any information from chapter 9 that you had questions about. And then I'll start reviewing for the final. We'll start going through the practice exam. And I have some big review packages that we can go through for each unit. So I have a chemistry review, I have a biology review, I have an earth science review, and some practice exams to look at. So we've got lots of things left, but this is the end of the new material. All right, so I'm going to power through this, 20 minutes, and then we'll go over all the questions you might have next day, and then we'll start review next day. So, We've already talked about acceleration. The only thing new in this section is we're going to deal with some velocity time graphs. Do we have a final? I haven't decided if I want you guys to write a practice final or not. You guys definitely have the provincial for sure, but I'm kind of on the fence about a practice final. So we might do it, we might not. We'll see how I feel next week. So acceleration depends on the change in velocity. The smaller amount of time the change in velocity happens, the greater the acceleration. The larger the change in velocity time, the smaller the acceleration. So you can increase the stopping time, which decreases the acceleration. And if you decrease the stopping time, you can increase the acceleration. And this is, Ava, I'll get to your question in a minute, maybe at the end of this stuff. This is how airbag works in a car. It takes the amount of time your face would normally slow down in, which is by hitting the steering wheel, and it makes it happen in a longer period of time. You hit the airbag, it's a nice cushion, and it slows your face down. So it increases the amount of time it would take your face to run into the steering wheel. And that decreases the acceleration, which increases your chances of surviving, keeping your wonderful face intact. So this is how airbags work, the sort of the principle of airbags. Distance versus time graphs with acceleration and lines of best fit. I wanted to talk about a line of best fit, but I didn't get to it last day. So let's do that now. All right. 2 or 3 things. Line of best fit. When you do an experiment, you're going to get some data. Let's say we were trying to find your position as a function of time. So this is distance versus time graph still. And let's say I said, okay, at 0 seconds, you're at 0 meters. At 1 second, you were at 1 meter. At 2 seconds, you were at 1.9 meters. At 3 seconds, you were maybe here. And at 5 seconds, you were up there. Now, these are all discrete points, meaning they're all individual points. A line of best fit is a way to average your data out. So if I were to draw a line of best fit with these points, I would try to draw a line that went through as many points as possible. I repeat, I do not want to connect the dots. In Physics 11, we don't connect the dots ever. Bad, 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 bad. Same with Science 10. Don't connect the dots. A line of best fit is going to be a line that hits as many points as I can, and the other thing is it should have as many points above the line as it does below the line. So in this case, I'm probably not going to be able to go through all of these points. I'm going to draw a red line here. There's a red line. I'm going to draw a blue line. And maybe draw... I'll just leave those two. Which one's better, the red line or the blue line, and why? It's kind of one of these really basic sorts of ideas. 2 lines I've drawn, they both kind of represent the data. One is maybe a bit better than the other. So I can't go through all of these points with a straight line. If I look at the red line goes through 1 point here, and it goes through another point here. So it's going through 2 points. My blue line is going through 1 point here and 2 points here. It's going through 2 lines. My red line has 1 point below the line, red, and another point below the line. So I have 2 points below my line. How many points do I have above the line? Up here, I have none. So because I have these 2 points, this guy here and this guy here, below the line, that's not a very good line of best fit, the red one. And it's not good because I have 2 points below my line. Whereas if I look at just the blue line here, I'm going through, I'm just missing that one, but pretty close. I've hit 3 points, more or less, and I have 1 point below and 1 point above. So the blue line would be a good line of best fit because it goes through as many points as possible, and you end up with points above and below. That's kind of what a line of best fit is. Sometimes you'll end up with a situation like this, where you have, I'm just going to draw a second, get all these points in a really great line, and then you end up with some goofy point that doesn't fit on the line. And this is a way to account for error in our calculations. It's going to be really hard to draw this. I don't have a ruler, but I'll do my best. So it's a straight line that accounts for as many as possible. This 1 point is probably a mistake. I maybe didn't make a good recording on my ruler or something like that. It's an outlier, which is fine. It happens. That's why we do experiments, to try to get an average. So a line of best fit for that second example, that would be fine. Basically, when you are taking recordings and measurements, your points are going to be all over the place because there's error. You're reading a ruler, you're measuring time, did you press the stop at the right time? And a graph is a great way to kind of eliminate some of the error as a result of your missed sort of calculations. All right. The actual point I wanted to show you here, the reason I showed you these two examples is because on provincial exams and in the curriculum, it says you need to know what a line of best fit. And it's just kind of, I've seen questions on provincials that look like, this. And they show you a bunch of different lines on graphs and they say, which one's the best fit line? And you need to pick the best one. So, two questions here I'm getting at. How should the best fit line have as many points going through in equal amounts on either side, or can there be more on one side than the other? There can be more on one side or the other. Imagine if I had another point, maybe right there. Now I have 1, 2 above the line and 1 below the line. If it still looks like a line of best fit, that's fine. You can end up with 1 or 2 below the line. Just like here, I have 1 below the line and 0 above the line. That's fine. There's no rule that says there has to be as many above as below. You want to go through as many as you can and kind of average out your data. And there's no rule that says you have to go through the origin. If you had a scenario like this, where these are your points, and you wanted to draw a line of best fit through that, you don't have to go through the first point. There's no rule that says the first point is more important than all of the other points. Go through the first point. No, you don't have to. So the first point is no more important than that point there. So lines of best fit don't necessarily need to go through the first point. Sometimes we think that they do. They don't. Another question. So even if it isn't uniform motion, do you do a curved line? This is what we want to talk about. This is why I had these graphs. Distance versus time graphs. For accelerated motion, yes, those are GIFs, and there will be a gift on your test in the physics unit for sure. Distance time graph. Now, on a distance time graph, if I had something that was traveling at a constant velocity, it would be a line like that. What if my object is speeding up? So imagine I have an object that's going at a constant velocity, and then it goes a little bit faster. Now I have a steeper slope, and then a little bit faster. What we end up with, if an object is speeding up, instead of having a straight line, you're going to have a curved line. So let's imagine an object, it's not moving. It's not changing its position at all. Its position is stationary with respect to time. And then it starts to go really slowly. So I have a positive slope. And then maybe it goes a little bit faster. I have a steeper slope. And then it goes even faster. And then maybe it stops moving again. Maybe it starts to slow down. And then it stops moving. So on a position time graph, if I end up with Now imagine this is a nice curved line instead of these small straight lines. If I have a curved line on a position time graph, that means acceleration. As soon as I have a curved line on a position time graph, that means the object's changing its velocity and it's accelerating. The object, you would end up with an object with a constant slope like that, Alex, because terminal velocity means that the velocity isn't changing. So that means the slope isn't changing. Slope of a position time graph is your terminal velocity. So again, getting back to the idea where the object moving in real life doesn't look like anything on a graph. We can't translate an object's movement in the real world to a graph directly, just because it's reached a constant velocity. Just be like you driving in your car going 100 kilometers an hour. Well, you've reached 100 kilometers an hour, your velocity is not changing, it's going to be a straight line. So anytime you see a curved line on a position time graph, that means the object's accelerating, speeding up, or slowing down. One thing that we can do is draw something called a tangent line. So if I wanted to know how fast the object was going at 2 seconds, I would go up, I would find that point. Now I need to take the slope of a line that only has 1 point. So what I can do is I can draw a line that only touches the graph at 1 point. That is called a tangent line. Now, the Learning Guide makes a big fuss about tangent lines. Tangent lines are an idea that are introducing a calculus topic, essentially. And you'll talk about them in Math 11 and calculus. They're not a big part of Science 10, but they do kind of help you understand what's going on. So if I wanted to figure out how fast the object was going and I only have 1 point to deal with, because it's a curved line, I can take what I call a tangent line, find the slope, and that will give us the velocity. All right, I'm going to continue on here. So we drew some graphs. Example 2, how can you tell easily if there's acceleration on a distance versus time graph? You have a curved line. And there's another example. The velocity getting bigger or smaller, what is the velocity at the end of the trip? So this gets back to this idea. We talked about tangent lines in Math 10. I don't even remember that. It seems so long ago. Is the velocity of this graph getting smaller or larger? What do we think? Remember, the velocity of a distance time graph is the slope. So is my slope increasing or decreasing? Is my object speeding up or slowing down? If I were to look right here at this portion of the graph, that's a steep slope. Then I were to look right here, that's less steep. And then if I were to look right here, that's even less. And then right here, this bit is horizontal, which means it's not moving. So because my slope is becoming less and less, this object is slowing down. Or has negative acceleration. Okay, let's look at some more examples. Consider this distance versus time graph. Is the velocity getting bigger or smaller? What is the velocity? Graph doesn't go through the origin. What does this tell you? So this is kind of the opposite. I have a very low velocity, and then if you think about drawing tangent lines, the slope is increasing. Means speeding up. And the velocity at the start of the trip. So I'm starting here. It doesn't go through the origin, which is where the axes intersect. What does that mean? Well, it just means I've started to the right of some object. So I'm not starting at the object. So the famous example I've been doing is a tree. It just means I've started my trip just to the right of the tree. Here's my little car. So I haven't started at the tree. I've just started, 2 meters to the right of the tree. And then I'm speeding up. Zoom. All right, now I'm gonna mess with your brains a little bit. Considering the distance time graph, is the velocity getting bigger, smaller, and what is the velocity at the start of the trip? So I think about my slope here. So I have almost zero slope, then it gets steeper, and then steeper, but my slope is negative. And it's getting larger. In terms of a negative. So what does that mean? Well, in this case, I'm just speeding up, but I'm going backwards. My slope's getting larger. It's getting more steep, but it's negative. So speeding up, going backwards. All right, I'll just talk about this velocity versus time graph and a couple important points, and then I'll leave you guys for the day. There are a few more slides that just have additional problems, but I'll go through a bunch of problems with you guys next day. We'll have some time for sure. So we've talked about distance time graphs, and I warned you that we'd get to a point where velocity time graphs appeared just as often as position time graphs, and now we're at that point. So the velocity time graph is different than a position time graph. Don't think that they're the same. Don't think that they're showing you the same information, because they're not. If they were, we would just have one. So the motion of an object with changing velocity, an object that's accelerating, its velocity is increasing or decreasing, it's changing its velocity. On a velocity time graph, it isn't a curved line like it was on a position time graph. On a velocity time graph, the way we describe acceleration is say, okay, at 0 seconds, you're traveling at 0 meters per second. Can't see these numbers. At 1 second, you're traveling at 12 meters per second if I go across. At 2 seconds, you're traveling at 25 meters per second. At 3 seconds, you're going 37 meters per second. At 4 seconds, you're going 50 meters per second. So this object is accelerating. It's increasing its speed. And on a velocity time graph, that is just a straight line. If this were a distance time graph, if I change this axis to a D and I wanted to show the same motion, I could, but it would look something like this. I would have 0, and then it would be doing this kind of increasing velocity if it were a distance time graph. But it's not. It's a velocity time graph. The slope of a distance time graph was velocity. The slope of an acceleration time graph, the slope of a velocity time graph is acceleration. So if you are asked to find the acceleration from a velocity time graph, you need to find the slope. And what if it started accelerating faster? Then if its acceleration was changing, you would see a steeper slope. And that's a completely sort of plausible thing for physics 11, but in physics in grade 10, you'll have things with constant accelerations. It would be a curved line if you were changing your acceleration. That's completely true. So you'd end up with, a steeper slope or a less steep slope if you change your acceleration. We'll start to deal with those sorts of things. You'll never see a curved line on a velocity time graph in Science 10, but you will see lines of different sort of velocities. So if we wanted to find the acceleration of this object, we'd pick 2 points. So you can see these ones have been isolated. 50 minus 25 over 4 minus 2. 25 divided by 2 gives us 13 meters per second squared. Watch your units. Slope is rise over run. Meters per second divided by seconds gives us meters per second squared. Now, I mean, realistically, that's all the nuts and bolts of this stuff. So kind of ran a little bit short on time, and I don't want to take you guys any longer than we need to be here. So that's kind of it. Next class, what's going to look like, I'll see you guys on Tuesday again. We have an hour. I'm going to go through any questions you had from Unit 9. You should be done Unit 8 by the time we make it to next class. Any questions you had from Unit 9? If you guys don't have any questions, I'll finish going through the notes. I think there's like 3 slides left. Just some examples and things like that. So nothing terribly earth-shattering. The next class we have is on Tuesday. And then on Wednesday, we're going to go to KSS at first thing in the morning. So at 8:45, meet me at KSS. We'll do a lab. Be lots of fun. And then I won't see you guys again for till the following week, which is actually the last week of, well, second to last week of class. So from here on out, we're going to finish up Unit 9 next day. We'll have some review material I'll have for you guys, and then we'll just be preparing for the final exam. When would I like this unit in by? I won't see you again until next Tuesday, so if you wanted to bring it to KSS next Wednesday, that would be great. I'll hope that you're done this stuff by Wednesday next week. Test written by the end of next week. So Unit 8 is this week, end of next week's Unit 9. Hopefully that gives you a time frame you can work with. How far in the learning guide can you go? You can do the whole darn thing now. We have covered every topic in the learning guide. What are the common units for displacement? You guys should do that. Some word problems can be a bit tricky. Throw a rock into the air, so objects in free fall. Just kind of positive, negative, circle the one. Graphing with acceleration, you guys should be able to do that. Yeah, you guys are good to go now for the entire Unit 9 learning guide. So finish Unit 8. Once you're done that, finish Unit 9. If you have questions on Unit 9, we'll answer them next day. Next Wednesday, we'll be at KSS. Everyone should be there. It'll be lots of fun. And then we'll just start reviewing. So hopefully that's all right. If you guys run into any problems, send me a message. I'll get back to you. And Abby, I will mark your Unit 8 right now. Thanks, guys. We will see you next week. Bye.